I'll just give you a one. I come from northeast England, so I try to moderate my accent, but it might sound a little bit strange to some people. The presentation's on NDT, investigation of PT ducts, and here you can see the learning objectives, so you should be able to understand at the end how we can use GPR and ultrasonic pulse echo technology to locate tendon ducts. Then we'll move on to show why pulse echo technology is better suited to detecting grouting defects. The reason behind this, there's actually two main parameters which are used to detect grouting defects. And finally, we'll look at the limitations of using pulse echo technology. So looking at the first point, which is GPR and pulse echo and how they can detect grouting defects. We detect objects in concrete because we get a reflection at boundaries between two materials. And in the case of pulse echo, the amount of energy that's reflected, it depends on the acoustic impedance of each material. It's a similar case for GPR, but then it's actually dependent on the permittivity of the concrete and the permittivity of the second material. And there's simple equations to calculate the amount of energy that's reflected. Looking at pulse echo, these are acoustic impedances for typical materials we're concerned with: air, concrete, steel, and I've taken plastic HDPE as well. So we can see here at the concrete air boundary we get almost 100% reflection of the signal. Concrete steel we get about 45%, and concrete plastic we get 37%. So what this means, we have a total reflection at the concrete air boundary, we get a partial reflection at the concrete steel boundary, and a partial reflection at a concrete plastic boundary. If we look at GPR, these are typical permittivity values, and it looks a little bit different. Concrete air, we have about 38%, concrete steel, we have 100% reflection, and concrete plastic, 20%. So basically here we get a total reflection at the concrete steel boundary and a weak reflection at the concrete plastic boundary. So why we look now at why pulse echo is better suited for detecting grouting defects. If we look at a GPR signal, we get a total reflection from steel, as I've just explained, so we get a sharp imaging of the rebar structure. We also get a total reflection from steel sheets, so it's very good for detection of PT ducts, but it's impossible to detect voids beyond the steel sheet. With pulse echo, it's different. We get a partial reflection from the PT duct. It means also we can see through steel, so if you have denser rebar structures, you can still see through to the sheets. Also, you can see from the position, pulse echo has a greater penetration range. GPR, you're talking down to about 50, 60 centimeters. I'm trying to think what that is in feet. I think it's about 2.5 feet, something like this. With pulse echo, you're talking about down to 1 meter depth easily. And yeah, because we get a total reflection from air, we can actually detect the presence of voids beyond the steel sheath. As I said, there's actually two parameters which allow us to detect grouting defects using pulse echo technology. If we look at a fully grouted duct, you can see here we get a partial reflection. And if we look at a duct with a void, we get a total reflection. So basically, we get a weaker echo from a fully grouted duct, and we get, if there's a void inside the duct, we get a very strong echo. So this is the first parameter that we can see. And we've demonstrated this principle. This is actually a test block we have made up, which has a metal sheath PT duct, fully grouted in part of it and partially grouted in the second half of it. This is actually what a pulse echo instrument looks like. This is an 8-channel instrument, and you can see it in position above the tendon duct. It's, in this slab, it's 18 centimeters depth. So if we look at the scan, this is basically directly a line scan directly over the tendon duct. And you can see here, we see 16mm rebars. They're at the depth of 4 centimeters. In this section, we get a very strong echo from the non-grouted tendon duct, and here we get a weak echo from the grouted tendon duct. So you get quite a clear differentiation. This is actually a sidearm example to show how this technique can be improved. The image I showed before was actually a B-scan, and this was actually done on site. It was an area we knew there was a grouting defect that had been opened up to prove this, and then we tested for comparison at a section where it was fully grouted. And here are the B scans at each section. So location A, this is with a known void, we get a very strong echo. Location B, you get a weaker echo. It's maybe not quite so clear, but actually if we combine B scans, so we scan in the bottom left there, you can see we scan basically perpendicular to the duct to make a number of B scans, and then we can interpolate this to create 3D images. And then you get the C scan, which is like in GPR they talk about the time slice, so we can actually, if I go back to the previous one, it's a perpendicular slice parallel to the surface at a particular depth. And now you can see a big difference between the two. So this is the C scan on the left with the void, and on the right fully grouted duct, and it's very, very clear the differentiation in this manner. There's a second parameter which can be used to convert the presence of voids, and that's actually to do when you have a reflection at a boundary. Depending on the acoustic impedances, you get a phase shift. So if the second medium has a higher acoustic impedance, there's no phase change. If it has a lower impedance, which air does, then it has a phase change. So if you can detect this, this helps you to confirm what you're actually looking at. And this is actually some testing. This was actually carried out in Japan by NEXCO, which is the sort of highway authority. They're doing large-scale testing to, with a view to implementing this technique. And then above, this is a typical B scan, where we have the grouted and non-grouted section with a weak and a stronger echo. And below, actually, we have, this is a phase diagram. Basically, we give a color code depending on the phase shift. And you can see there's a big difference on the right-hand side and the left-hand side. So this gives an added, what should I say, determination of the presence of voids. These methods are actually not new, I would say. The main research was done in Germany by BAM, so the Federal Institute for Materials Testing. This is actually a report which was done in America by the highway authorities here, where they tried out all of the non-destructive evaluation methods for looking at voided systems. And these were the findings they found in basically for ultrasonic pulse echo. And the statement there is basically scanning with ultrasonic echo together with phase evaluation is capable of identifying grouted ducts in plastic and metal ducts. The equipment you see on the bottom right, it's like it carries out measurements in a tight grid, and until, I would say, it's still in basically research equipment. The technology, as I say, was mostly developed in Germany, and it's at the case now where it's sort of coming close to being available in commercial instruments. There are, however, limits to this method, and actually this is the main issue here. If we have a large grouting defect on the left, and we have on the right hand side, we have just a delamination because the grout is not correctly connected to the sheath. We get a thin metal layer. We will get a total reflection from the air boundary from both cases, so we cannot actually differentiate between these two cases. And this is actually, there have been some cases of this. I know from personal experience in Germany where they've had this issue. So that's actually one limitation you have to be aware of. So in conclusion, pulse echo technology is capable of detecting grouting defects. 3D imaging on site and phase analysis in commercial equipment, it's in sight, it's not yet implemented. Actually, there is no commercial equipment available right now that has all of these capabilities. But the benefits are, of course, NDT. You can make a comprehensive evaluation, which you can't do by making openings in the concrete everywhere, of course. The test will no longer be limited to research institutes, and basically you can get an immediate evaluation on site. So that's it. Thank you very much. And